Relations and functions. We want to start out by defining some of these basic terms. The first term we're going to look at is relation, which is any set of ordered pairs. Now you should be familiar with these XY coordinates as you see below, but it can mean any number of things. It doesn't necessarily have to be numeric. You can have a relation with students in the class compared to students in another class. It doesn't always have to be XY coordinates like we're used to. There are different ways to represent the same relation. The first way that you can see is just a table. You can list all of your one variable on one side, all of the second variable on the other, and then you can see the same coordinate pairs that we were looking at are shown in table form. The second way that you can list this is a mapping diagram. In a mapping diagram, you have the domain in one box, the range in the other, and then you will notice that there are arrows going from the domain to the range on the other side. What you do notice is that you do not list the numbers twice. So even though 4 is used with -2 and with +2, you're only going to list this one time. Typically, when I have you do this, I will also have you list this least to greatest. The third way is a graph. On the coordinate plane, you can list these XY coordinates, your x-axis, your y-axis, and then list the coordinates accordingly. Let's talk about domain. So domain is the set of first elements in the ordered pairs of a relation. So in this example here, your domain would consist of those first numbers there. So you would have the 4, the 1, the 0, and again, you don't list it twice, and you will also want to list these in least to greatest order. So I would take this and I would write that domain in set notation as 0, 1, and 4. Range then is the set of second elements in the ordered pairs of the relation. So when you look at this, again, if we're talking about the range, you would list just the y coordinates or the second coordinates in these ordered pairs. So then let's talk more specifically about a type of relation called a function. This word is very specific to a type of relation where every first coordinate has one and only one second coordinate associated with it. I like to say it's a one-to-one relationship. So this example here is not a function because we have some x's, or we have the first coordinates that not only have one y coordinate or second coordinate, they also have a second one. So this 4 maps to -2 and to +2. And secondarily, we have a 1 that maps to -1 and +1. So this is not a function. If we look at these, we're going to determine, is this a function or is this not a function? And as we look across it, we are going to check those. We have a 3 has 1, a 4, a 5, and a 6. My first coordinates are not repeated. This is a function. But we look at the second one, we have a 1 to a 3, a 1 to a 5, a 1 to a 9. This is not a function. Another way that you can tell if something is a function is to look at it on a graph. And on a graph, you should be able to see if it is a function or if it is not a function, because you can tell whether the coordinates have two different y values. If I look here, this has 1, but if I look at the x value of 1, you can see there's 2 y values. The x value of 4, there's 2 y values. And this is referred to as the vertical line test. If 2 or more points of a graphed relation lie on the same vertical line, the relation is not a function. So if you were to draw a vertical line anywhere on the graph, you should cross it one and only one time if it is a function. So if we're looking at this to determine if it's a function, You can see this vertical line here crosses this more than one time. This particular one is not a function. However, when we look at this one, no matter where we would draw this particular vertical line, it would only cross this function once, and so it is indeed a function. So just some basic examples of a function. If we are trying to decide if these two are functions or not, you could draw a vertical line. Clearly it crosses. Anywhere you would draw a vertical line here, it does not cross twice. So a couple of terms you may not be familiar with when we're talking about x and y coordinates are the official names of those x first coordinates, y second coordinates. The first coordinate is called an abscissa, which most of the time we will use the x for, and the second coordinate is called the ordinate, which we will typically use a y for. One of the things you probably have learned at this point is function notation. Function notation refers to, instead of using a y value here, you use f of x. That does not always have to be f. That does not always have to be x. This f is just a variable of whatever function you're talking about, and this x is just the input value of the function. And so when we talk about input, we now have to look at what's called a dependent variable or an independent variable. And in this case, the independent variable is always the one that you are inputting into the function. So when it is function notation, the independent variable is inside that function notation. So counter to that, you have a dependent variable, which is often called the output of the function, and that is this f of x. If it is in standard notation here like this, you're going to have that y variable as your output. So when you look at this 5 and 8 coordinate here, the 5 represents the input of that, the 8 represents the output. So the 5 represents the independent variable and the 8 represents the dependent variable. So let's look at graphing. You are going to recognize some of these functions, but we're going to go back to the basics of graphing these functions. And so if I were to graph this particular parabola, I could just pick some points, solve for them, and graph. If I take a 0, I could plug that in. 0 squared plus 1 is 1. That is going to be my first coordinate here. If I were to take another one, let's just say 1, plug that in. 1 squared plus 1 is 2. You're also going to find that if you plug in a negative 1 and you square it, you are also going to get 2 there. And if we do one more, let's say 2, we square that. 2 squared plus 1 is 5. Also plugging in a negative 2, we will get 5 as well. And so if we graph those, you're going to see that you have this parabola. Now, when they don't tell you anything about the function, you're just going to look at this and say, I could keep going indefinitely with this. And you would sketch that graph and make that assumption that you just keep going indefinitely here. However, there are times when they are going to restrict you with your domain, which we talked about, were your x values, right? Or your input values. And so your x values here, if they limit it and they say, well, we want you to only go from -2 to +2. And just as a refresher, they used a less than, not a less than or equal to. We have to do two things with this graph. First of all, we can't just assume that it goes on indefinitely because they have told us, no, we want you to limit it. And then the other thing is they did not do an inclusive here. So instead of points on the end of that, we are going to use open circles on the end of that. And that indicates that we are stopping at those 2 points, and those 2 points are actually not included in it. And so just a little refresher from prior courses that you do need to remember kind of the ins and outs of whether something's included or whether it's not. So there are two ways to indicate that domain, that X value that we talked about. The first way is that set notation. To define that, we're going to define the variable that was the input variable or was our domain variable. X was that variable we were talking about. You're going to draw this line. When you read it out mathematically, you're going to say X such that. So this line right here represents the words such that, because you're about to define X for the reader. And you're going to say, well, X is between -2 and +2. And by the way, we're not including them because we didn't do an or equal to. The other way that you can write a domain is called interval notation. Interval notation literally just writes the interval. So if we were to use the interval 3 to 5, let's say we were going to do that instead of -2 to +2. There are three ways to do that: closed, open, or you can be half open and half closed. Closed would be equivalent to or equal to. So if I were to rewrite this in set notation, I would say, well, my X is between 3 and 5, just like the 2 and -2, but I'm going to use or equal to. That's what that bracket means for closed. Open then would be the same numbers. X is between 3 and 5. But in this case, we're not going to use that or equal to. So that's what those parentheses mean. And then the half open includes one but does not include the other. And so if you were to write this, you would actually say that the 3 is going to be or equal to, and the 5 is just the less than there. And so that's what an interval notation. It's just a shorter way of writing maybe a set notation. So then let's look at this in what's called bounded or unbounded intervals. So with bounded intervals, whether it is open or closed or half open, they have numbers on both ends, meaning A and B represent a specific number. And so you could have any combination, both closed, both open, the left side closed, the right side closed. You also have what's called unbounded. These are when you have a greater than a number and one side goes to infinity, or a less than a number and the other side goes to infinity. And so anytime you have infinity in your boundaries, it is going to be open on the infinity side, because infinity is just a concept. It's not an actual number, so you cannot include it in your interval. And so, for example, we have X is greater than or equal to A. It means it starts at A and goes infinitely larger than A. It could include A or not. If the variable is less than a number, then the low end is going to be the negative infinity, and you're going to go up to that number. Again, it can include it or not include it. And so this is the difference between bounded and unbounded. Bounded means I have two numbers. Unbounded means I have an infinity in there. Just to review the different types, in a graph, you're going to see closed and open. Similar, if you were to do this with a number line, you would see a closed circle or an open circle. If you were to convert that to an inequality, closed would be or equal to, open would be just the less than or greater than. And then interval, the closed would be a bracket, the open would be the parentheses. For unbounded, you're going to have an arrow going infinitely in one direction or the other. Whatever direction it is, that's where your variable is. It is going to be less than if it's going to the left. It's going to be greater than if it's going to the right. And wherever that direction is, if the number is the largest and your variable goes smaller, then you're going to start at negative infinity. If your number had been the smallest and it went to everything larger than that number, you would have used positive infinity. But remember, unbounded, with infinities, you always have the open. You don't have a bracket there. So let's just do an example of this. Write each inequality in interval notation, then graph the interval on the number line. So I'm going to drop a number line in here, and I'm going to start with A. If I were going to write this in interval notation, I'm going to first notice that I have just a less than and a less than or equal to here. And so for this one, I am going to write an open parentheses here, -1, comma, +3, and a bracket. On the number line, it would look like this: an open circle on that 1, a closed circle on the 3, and everything in between is shaded. For the second one, my variable is larger than that 2, and so we're going to start with the 2. It does include the 2, so we're going to do a bracket, but now we're talking about everything bigger than 2, so that's going to be a positive infinity, and of course that is open. And so on the number line, again, we would do a closed circle at 2. We would go everything larger than 2, and we will just put an arrow there. That's what that would look like. If I were to put this in set notation, then for this first one, my set notation would be an X, and then I would just repeat that interval just like it gave me in the inequality. It looks just exactly the same. And the same thing here, if I were to do set notation, it is the same thing as that inequality. Looks just like that in set notation. So when you think about domain of a graph or range of a graph, remember the domain represented all the x values, the range represented all the y values. You have to look at this as, is anything taken out of it? So if I were to look at the x values, I'm going to say, well, it starts all the way here with an arrow. That's a negative infinity. And it looks like it goes all the way over here, positive infinity. But I can't just go from negative infinity to positive infinity here. And that is because I clearly have a break in the graph. And so when you do that, you're going to go back in your brain when you used to do intersections and unions, probably started that in like your geometry era. You're going to use those unions and you're going to say, well, I know I go from negative infinity, but something happens at 0 on the x-axis, and it clearly does not include 0. So I'm going to say 0, but I have that open there, right? But then I'm going to jump over 0, start at 0 again, and it goes all the way to infinity. If I were to look at my y values, well, again, you can see for the y, if I'm looking at y, right here at 0 again, I don't ever cross it at y either. And so as I'm traveling up, I can see that I go all the way from negative infinity down here, but at 0, once again, I don't touch 0. And I do jump over it, and I go all the way back up. So if I were to look just up and down, I start down here. I do travel up, but right here I jump over it, and I go up, and that's my y value. And if you look at it on the x value, I start over here at negative infinity. When I get here, there is no value here for x, and then I keep going. And that's why I'm using those unions. I'm just jumping right over that part that is not included in the graph itself to define that domain and range. And so sometimes instead of using that interval notation, set notation is easier, because I can really just say, well, it includes all x's except for 0. It includes all y's except for 0. And so sometimes it's easier to write your domain in interval, or sometimes it's easier to write in set notation. It just depends on what all you have to explain to the reader.